Okay, so good morning, everybody. Hopefully you had a good 3-day weekend to catch up on studying and relax a little bit. I don't know if you guys caught my video, but I did leave a video for you from my small studio apartment near Lake Merritt in Oakland. It's a nice area, beautiful area, and was able to do some nice jogs around the 3 Mile Lake. And at night, they actually have these lights that surround the perimeter of the lake. So it's really a beautiful area in Oakland. And I noticed also that they have the buildings, the government buildings there in that area. They are all lit up with the colors of the Golden State Warriors. Because they're all happy about the Golden State Warriors. There's like a fever going on over there about how good they're doing and how I guess they had some close calls while I was up there. They were about ready to lose, but apparently they made it to the finals. So I have at least one of my daughters is interested in how they're doing. All right. We will continue where I left off from the video that I left you. The video that I left you basically talked about the cholesterol metabolism, and it also talked about let's see, what else did it talk about? Oh yeah, fatty acid nomenclature as well. So make sure you review those aspects. I didn't get into a lot of detail about the synthesis of cholesterol. And so I'm hoping that the next instructor that takes over for Chem 431C will start you off there in terms of the synthesis of cholesterol. As a matter of fact, I will not have the time to go over fatty acid synthesis either with you. So I know that these are aspects of chapter 17, fatty acid synthesis and maybe cholesterol synthesis. And so I won't have the time to do that. We will talk about metabolism of those and control of the metabolism of fatty acids, as well as glucose again. So we'll return to that theme. Okay, I want to talk a bit about this concept called ketone bodies. And ketone bodies are small molecules produced from acetyl-CoA. So ketone bodies, small molecules formed from acetyl-CoA. And they can be used as alternative energy sources. What are they exactly? They are acetone, which is actually a minor component, so I'll just write down minor. They are also acetoacetate, and the third one is D-beta hydroxybutyrate. Okay. These are going to be synthesized in the liver. And so how exactly are they synthesized? Your book actually, I think, has this. Oh, by the way, they're synthesized specifically in the mitochondrial matrix. Okay. I think your book has a section where it talks about the synthesis, so I'll just go ahead and bring that up. here we go. Okay, so this is on page 735 of your book. So here is acetyl-CoA. There are two acetyl-CoAs here. I'm kind of showing you a mechanism where you take off a proton from the methyl group here of one of the acetyl-CoAs with a base, and you use the electrons that are there, the pair of electrons that are there, to do a nucleophilic attack onto the carbonyl carbon, and then what's going to leave eventually will be this this coenzyme A. Okay? And in doing that, you're going to get something called acetyl-acetyl-CoA. So this is what you'll get, acetyl-acetyl-CoA. And the acetyl-acetyl-CoA is going to have 4 carbons, 1, 2, 3, 4, from 2 different acetyl groups, right? And then the next step is to convert the acetyl-acetyl-CoA to 3-hydroxy, 3-methylglutaryl-CoA. So let's go ahead and go through that. And so here you can imagine that you're going to, let's see, how would this work? I guess you're going to take off a proton from this methyl group here, and it can perform a nucleophilic attack right here. And then that's going to create this 3-hydroxy methylglutaryl-CoA. Eventually, after that nucleophilic attack, you're going to have to remove this coenzyme A part using water. So water will make an attack right here on this acyl carbon, and the coenzyme A will leave. Let's go ahead and analyze this word, 3-hydroxy, 3-methylglutaryl-CoA. Let's see if this makes sense. So first of all, I don't know if you remember alpha-ketoglutarate. Do you remember that term, alpha-ketoglutarate? It's kind of warm in here, isn't it? Alpha-ketoglutarate. I'll let you guys think about where you may have heard that before. Beautiful, Krebs cycle or citric acid cycle. Okay, can't do that. I think, okay. All right, but that gave you guys a chance to think. Okay. Sorry. Alpha-ketoglutarate, right? And if you look at the number of carbons in alpha-ketoglutarate, you'll notice that it has 5 carbons. So glutaryl groups have 5 carbons in them. So let's count the number of carbons here. 1, 2, 3, 4, 5. That's the main chain right here. 1, 2, 3, 4, 5. So that's 5 carbons on the main chain. Okay, so this would be considered a glutaryl group. Okay, and then it says 3-hydroxy, 3-methyl. So here's the number 1 carbon. Number 2 carbon, number 3 carbon. Here you have a hydroxy group on the number 3 carbon, and also you have a methyl group. So 3-hydroxy, 3-methylglutaryl-CoA, HMG-CoA. So that's how we name that. Okay. The next step is to use water to go ahead and hydrolyze off this acetyl-CoA group. So we're going to hydrolyze off the acetyl-CoA using water. Let's see if that makes sense. So what's going to happen is that you're going to sever this bond. Actually, don't use water. This is a lyase. I'm not sure why I have water there. So this is a lyase. So no water there, okay? What's going to happen is that you will have a base that will remove that proton. The electrons from the oxygen is going to come down, and then this will attack an acid. Okay, and so now you're going to have this sort of acetyl-CoA group, and then you have acetoacetate. So acetoacetate is going to be one of your ketone bodies, okay. And then it's showing here that a CO2 group could leave from this acetoacetate, and you could make acetone. Anybody remember where a common product that you can buy in a beauty store that has acetone in it? Very good, nail polish remover. And so actually people that have ketone bodies, that are producing ketone bodies, you can actually smell a little bit of the acetone on their breath, okay? A little bit, okay? And then also, the third one, the third ketone body is beta-hydroxybutyrate. Beta-hydroxybutyrate, let's see if that makes sense. Beta-hydroxybutyrate. Okay, can you guys tell me, this is the number 1 carbon, number 2 carbon, number 3 carbon, number 4 carbon. Okay, good, it has 4 carbons, that means it's a butyrate, right? You guys remember that, okay? Which carbon number is the beta carbon? You guys got it right away. 3. Very good. So it's 3, right? Which carbon is the alpha carbon? Beautiful. 2. Excellent. That's exactly right. So here we've got beta hydroxybutyrate. So on the beta carbon, you got this hydroxy group. So these are the 3 ketone bodies that are made. By the way, this one, you have acetoacetate, and it's produced by adding NADH, and now you create beta hydroxybutyrate. Can anyone tell me the class of enzyme that performs this reaction where you go from acetoacetate to beta hydroxybutyrate? The class of enzyme. Is it a hydrolase? Is it a ligase? Is it a... Someone said oxidoreductase. Why? Why'd you say oxidoreductase? What was the dead giveaway? Very good. NADH, right? So very good. NADH typically means that you're going to have an oxidoreductase here. The other dead giveaway is that it said way here in red in small letters, dehydrogenase. Very good. So that's an oxidoreductase. Okay, so these are the 3 ketone bodies that are produced by the liver. The liver then dumps these into the blood. The acetone is very volatile, but in the blood, what happens is a couple of things. Number 1, does anyone know what the pKa is of a carboxylic acid, approximately? I'm not asking for the exact one. Approximately, pKa of carboxylic acid. 7. Not 7. Not -2. It's going to be about 3. 3, okay? So remember that. The carboxylic acid is always about 3, right? And so also you have another carboxylic acid here. You have a low pK as well, okay? So when these get secreted, actually they have a proton attached to them. But once they're in the blood, the proton comes off. And what's that going to do to the pH of the blood? It's going to lower it, therefore it's going to make it more acidic, right? And so people that are secreting lots of ketone bodies from their liver, we call that ketogenesis. That makes sense. Oh, by the way, these are ketones, right? Here's a ketone right here. there's a ketone. So we call this ketogenesis, but also accompanying that is something called acidosis. Acidosis, okay? And acidosis means basically that the blood is getting more acidic, getting more acidic. And that's because you have these acidic groups on two of these ketone bodies. I know this is not really a ketone, but it's considered in the class of ketone bodies because it came from acetoacetate. Well, how can these be used as alternative energy sources? The two main sources of energy are glucose and fatty acids, right? We've talked about that. This is a third possibility, okay? And what happens is that this gets back into the, for example, the brain, okay? So this can travel through the blood into the brain. And then basically what you can have is inside the brain, I'm not sure why they don't show these structures, but you have beta hydroxybutyrate getting oxidized in the brain to acetoacetate, and it's oxidized with NAD+. And then this sort of weird reaction where succinyl-CoA contributes a CoA group onto the acetoacetate to make acetoacetyl-CoA. And then once the acetoacetyl-CoA is made, let me go ahead and draw this for you. Thank you. So once the acetoacetyl-CoA is made, so in the brain, and other organs as well, but especially in the brain, you're going to have an attack with coenzyme A to produce these two products. And can anybody name this product right here? Acetyl-CoA, very good. And this one? So basically you're making two acetyl-CoAs. Very good. And the brain then can use this for energy. Can anyone tell me how you can get energy out of acetyl-CoA? Go through the Krebs cycle. And then eventually you can do oxidative phosphorylation. Exactly right. So the brain uses this as an alternative source of energy. Now, when does this happen? Because we've got the brain using glucose. You guys know that the brain cannot use fatty acids, right? Fatty acids are a no-no for the brain. But the brain uses glucose. It consumes the majority of glucose in your body. I shouldn't say the majority. Out of all the organs, it consumes the most glucose. Let's put it that way. Out of all the organs, it consumes the most glucose. But what happens when glucose levels are low? Let's say that you haven't had a meal for a while, and you run out of the dietary glucose that you have. Then the liver has to kick in and start to make glucose, and it makes glucose through two processes known as glycogenolysis, breaking down the glycogen, it also can produce glucose through another means besides glycogenolysis. Anybody know what that is? Beautiful. Gluconeogenesis. It's like music to my ears. Gluconeogenesis. Beautiful. That's exactly right. So gluconeogenesis. And gluconeogenesis is great as long as you have some source material, okay? But sometimes, and this happens after fairly long periods of starvation, what happens when liver runs out of OAA? Does anybody remember what OAA stands for? Oxaloacetate. So that's one of the important parts of gluconeogenesis, okay? So it runs out of OAA, okay? And so when that happens, then what happens is that if you remember, OAA plus something gets together in the citric acid cycle to make citrate. Okay, it makes citrate. Does anyone remember what X is? Acetyl-CoA. So what happens that if you don't have any OAA, then this X starts to build up, where X equals acetyl-CoA. Okay, and you start to get this abundance of acetyl-CoA, and then that's when you start to do ketone body formation. Okay? And that's important because the brain will still survive without any glucose in the bloodstream. It can still use the ketone bodies as a source of energy. And I just showed you that the source is really acetyl-CoA. That's broken down from the ketone bodies. By the way, the ketone bodies are also exported to other organs as well. So ketone bodies are going to be exported by the liver to the brain, the skeletal muscle, and heart muscle, renal cortex. So all these organs can survive during periods of starvation. Another source of the acetyl-CoA that, by the way, the acetyl-CoA that is made inside the liver, a source of that are the fatty acids. So fatty acids can be broken down in a process known as what in order to make acetyl-CoA? What is that process by which fatty acids can be broken down to produce acetyl-CoA? Beta oxidation. Exactly, beta oxidation. So there's all this rush to make acetyl-CoA during times of starvation in order to produce these ketone bodies, in order to supply organs with fuel. And out of all of these, probably the brain is most dependent on the ketone bodies. I think these other organs can use other sources like fat and like fatty acids. Okay. So I want to sort of show you what happens in a graphical form when we deprive our bodies of food for long periods of time. Okay, what did I do there? Darn it. Shoot. Okay. It's not much of a change there, huh? Okay. All right. So I'm going to draw a graph here. I think I'll start this on a new page. Okay. It's going to have 3 axes. It's going to have 2 y-axes and then an x-axis. And here we have millimole per liter. Here we have a period of starvation. And here we'll talk about insulin. So this is the insulin level in microunits per milliliter. Microunits per milliliter. Okay, and the scale here is going to be 0, 2.5, 5.0, 7.5, and then 10. The scale here is going to be 0, 10, 20, 30, 40, and that we're talking about days. Okay, so severe starvation. And then here we are at 0 for insulin, 0.5, and then 1.0. Okay. So we'll start off first with the ketone bodies. And as I said before, ketone bodies will start to rise during periods of starvation. So we get to approximately 5 millimole per liter at day 10. And then it starts to slope off just a bit like that. Okay. Glucose levels drop. Okay. And this is going to be ketone bodies. This one's going to be glucose. Ooh, cool. Glucose. Oh, that doesn't look very good, sorry. Glucose levels. And then I have this other line for free fatty acids. So free fatty acids are like this. And then finally, we have insulin, and insulin is going to drop precipitously like this. And so this is insulin. Of course, insulin is something that's secreted once we've had a meal. So imagine that we haven't had a meal for a long time, our insulin levels are going to drop tremendously. Okay? So this is what's happening under starvation conditions. That's why we depend upon ketone bodies for energy sources during long periods of starvation. Okay, I want to now take a look at my outline, make sure that I'm organized. Okay, I'm going to talk about metabolic interactions amongst organs. And so we're going to now go to chapter 18 because I want to start making connections with the stuff that we've learned. So chapter 18 is a good place to kind of see how everything is working together. So let's talk about page 755 of your book. This is page 755 of your book, which I think is a great diagram to demonstrate what's happening in our body biochemically with all these different organs. We're going to start off simple, then we'll get more complicated. So first of all, I had talked about how when we eat, materials go through our intestine. Okay, so I'm starting here at 6 o'clock on a clock. So down here where the intestines are. So, and we can absorb glucose. Okay, and also we can absorb triacylglycerols. And what's great about this is that it says right here chylomicrons, which is one of these lipoproteins that transport these triacylglycerols. Okay, so chylomicrons are going to go into the bloodstream. And we'll stop here at the first stop, which is going to be the adipose tissue. So I'm going counterclockwise in this sort of circulation pathway. And what you can see is that once it gets to the adipose tissue, there's enzymes on the outside of this adipose tissue that breaks down the triacylglycerols into fatty acids and also glycerol. Okay? And so the fatty acids get taken in, the glycerol gets taken in, and you recreate these triacylglycerols inside the fatty acids. And I guess, I'm sorry, not inside, inside the adipose tissue. So the triacylglycerols are made inside the adipose tissue. The other thing that happens is that in order to survive, the adipose tissue itself can undergo a little bit of beta oxidation in order to keep alive. Okay, so they undergo some beta oxidation. And also glucose can be absorbed by the adipose tissue as well. What else? The fatty acids can travel to the heart, okay, so the heart muscle. And in the heart muscle, it can undergo beta oxidation as well. The glucose, of course, can undergo glycolysis and citric acid cycle. And I won't talk about the ketone bodies just yet, so let's hold off on these ketone bodies. Okay, for the glucose that we get from the diet, of course it's going to feed the brain, and the brain undergoes glycolysis and citric acid cycle. Also, we have the striated muscle. So this is the muscle in our arms and our legs, okay? And so here we have fatty acids that can undergo fatty acid beta oxidation in order to give our muscles some energy. And also we have glycolysis occurring as well. By the way, the muscle can store some of the glucose in glycogen, okay? So we have glycogen synthesis occurring here. Sometimes called, glycogen synthesis. Okay, and then finally we've got this thing called the liver, which is the big powerhouse that basically makes sure that all the other organs are well fed. Okay, and so we've got glucose coming into the liver, and it can undergo glycolysis as well as glycogen. It can create glycogen as well. So the glucose can do all that. And then fatty acids also get transported into the liver, and it can undergo beta oxidation. And it can also store the fat in the liver. Some fat does get stored in the liver as well. Okay, so we've got the triacyl glycerol. So this is the dietary stuff. Well, what happens when you're between meals? Well, when you're between meals, the liver then can mobilize glucose, okay, and it can take it out of the glycogen stores, and it can supply that to the other organs. The liver can also undergo gluconeogenesis, and it starts from lactate. The lactate which is produced from the muscle, okay, so the muscle can produce lactate through glycolysis. I'm not sure why they have this under proteolysis, but the lactate can be produced from the muscle, and the lactate will travel through the blood and go to the liver. The liver then will produce glucose from this and then resupply all the other organs with that glucose. Does anybody remember what cycle that is, where lactate is being produced by the muscle, and then sends it to the liver, and the liver then produces that glucose and sends it back to the muscle? Anybody remember the name of that cycle? Long time ago we talked about this. Starts with a C. The Cori cycle. Very good. Excellent. The Cori cycle. That's exactly right. So that is the Cori cycle. Okay, wonderful. Right. Okay. And of course that lactate, which is being produced by the muscle, occurs because we need to regenerate NAD plus in order to keep glycolysis going, right? We talked about that. Okay, and then we talked about ketone bodies just now. And so ketone bodies can be produced by the liver, and these ketone bodies can then be sent to other organs, especially the brain, but other organs can use these ketone bodies in order to use those as alternative energy sources. Now, we didn't get a chance to talk about proteins as a source of energy, but also under starvation conditions, you can proteolyze your proteins down to amino acids, and one of the amino acids that's produced is alanine. And alanine can be, alanine can be converted into pyruvate, and then it can also be produced, and also that can be converted into lactate. That's true. Okay, so now I understand this. Okay, and that can also be used as an alternative energy source because that lactate then can be sent. The alanine and the lactate can be sent to the liver, and the liver can then use that to make glucose through gluconeogenesis. So you can see even proteolysis to produce alanine. Let me just draw for you alanine. Show you how that is. I know we haven't talked about proteins that much in this quarter, but let me go ahead and draw for you alanine. So alanine. That was a bad beginning. Okay. Okay, and this can get converted through something called a transamination reaction. Okay, and it can get converted into this. Okay. And does anybody recognize what that molecule is? See if I can recognize it. Okay, I think I got it. What do you think that is? No, it's got 3 carbons on it, so bicarbonate has 1. Glycerol has 3 carbons on it, that's true, but it's not glycerol. Glycerol has 3 alcohol groups on it.
What's the first letter?
Oh, come on, I'm going to give you guys another minute to think about this. How about if I draw it another way?
Yeah, draw it OChem style.
OChem style. Not sure if this is OChem style. I got some time.
It's part of the citric acid.
Excuse me?
Is it part of the citric?
Citric acid, no, it's not part of the citric acid cycle, but I'm,
Or glycolysis.
you guys are thinking. This is a very simple molecule, right? We must have encountered this some other way. Some of you may know it, but you're not saying it. Bring out your voices.
Is in glycolysis?
No, not strictly in glycolysis. It's not in glycolysis. So alanine can be converted into this, and this can be used by the liver in order to make glucose. Someone said it. I think they said lactate. Yes, this is lactate. Come on, guys, this is lactate. Okay, and if I oxidize that central carbon, what would I produce if I oxidize the central carbon? Let's pretend I have an enzyme that can oxidize that. Pyruvate, very good, very good. So this becomes, we can oxidize this. Does that look familiar? Yeah. Oh, well, it shouldn't look familiar. I didn't make that right. Sorry. That was wrong. Let me get my eraser. There we go. Okay. So that's lactate. Okay. Maybe you guys should know lactate for the exam. Okay. All right. And so anyway, alanine can also be easily converted into lactate, which can be converted to pyruvate, and that can be used for gluconeogenesis in the production of glucose or energy consumption. So we've got a number of these things going on here. Let's see here. The only thing that I didn't talk about was glycerol. So glycerol can also be taken in by the liver. That's part of triacylglycerol. So you can take in glycerol, you can take in fatty acids, you can create triacylglycerols from the glycerol and the fatty acids. And then we have this other material, VLDLs, which is a way of delivering fatty acids to other parts of the body. Okay, so these VLDLs, that's a lipoprotein. All right, so we kind of see how all these interactions are working, and we can bring in a lot of biochemistry to fill out these words. So these words, they're words, but you should be thinking about them in terms of chemicals, right? So you should be what should be floating in your mind here are chemicals. Okay. So I want to talk a bit about diabetes, because that's a good place. This is a good place to start talking about diabetes and the discovery of insulin. So we'll talk about diabetes here. And basically, the story starts with 1889. Around the turn of the last century, the Germans were strong in chemistry and biochemistry. I mean, they're still strong, but they were solely strong. I mean, they were the strongest in the whole world in terms of this type of research. And so in Germany, there was a physiologist. His name was Oskar Minkowski. Okay. And somebody else by the name of Joseph von Mering. They were studying the famous, the typical mammal that was used for experimentation around the turn of the last century. Does anyone know what that mammal is? Not pigs. We talked about this animal before. Dogs. Okay, so dogs were like a major organism that was used, and so what they did, they were studying digestion, and they performed a surgery where they would remove the pancreas. Okay, and somehow these dogs survived, I guess, after removing the pancreas. Okay, and they would, and because they knew that the pancreas was secreting enzymes that were important for digesting food. Okay, so lipases, for example, are made in the pancreas. So they were studying digestion. They removed the pancreas from dogs. Okay, and they found out that when the dogs, I guess they used to house the dogs in the laboratories back then. Okay, and they found out that when the dogs urinated, okay, the urine would attract small insects. Okay, so attracted ants and other small insects. And they said, well, that's kind of weird, because most of the time, I guess they've had experience with dogs urinating, they wouldn't attract that many ants. And so they realized that, and I'm not sure how they performed this experiment, but that the urine had a lot of sugar in it. Okay, so the urine had glucose. Okay. And finally, they realized that there was a connection between the pancreas and glucose. And they figured out that the glucose was not only high in the urine, but the blood also had high glucose. And so what essentially they were doing is that they were taking away the ability of the dog to absorb glucose from the urine, from the blood. And finally they figured out that there was a hormone that was inside the beta cells of the islets of Langerhans. In the pancreas. Okay, and those beta cells are the producers of insulin. Pancreas. Okay. Many people afterwards went on to purify the insulin, and when they injected insulin into dogs with no pancreas, what happened is that the urine did not have glucose anymore, so then no glucose. So they could make that effect go away in urine or blood. So that was their experiment. The condition that these dogs had was diabetes, because they were unable to move their glucose from the blood into the organs. And we now know that there are two main types of diabetes. There's something called type 1. And in type 1, there are no beta cells. Okay? And therefore, these patients fail to produce insulin, and it's thought that the beta cells are destroyed through something called an autoimmune disease. Okay? Destroyed via autoimmune disease. And I talked about how important it is that our T cells become educated in the thymus during development. And in some cases, these T cells and other immune cells can destroy your own bodies. This is that case, autoimmune disease, and type 1 diabetes is thought to arise from this problem. Type 2 diabetes is much more common. Okay, oftentimes called adult onset. And in this case, oh, by the way, this is also called diabetes mellitus. Diabetes mellitus, okay. And what happens at secretion, that's cool, okay. Secretion of insulin is okay, but cells do not respond. In obese patients, obese people, this is very common. The inability of the cells to properly respond to the insulin which is being secreted. Therefore, a fairly high percentage of obese and hyper-obese people have type 2 diabetes. We're going to stop here. I will continue with the relationship between diabetes and ketone bodies and starvation. We'll talk about AMP-dependent kinase, and we'll have a kind of a course review at the next time that we meet. So I'll see you then. Have a good day.